Hey guys, so this is the continuation for the lectures in signals and systems. I will focus in this lecture on three main signals used in medical imaging. So we have point impulse, line impulse, and comb and sampling functions. These are the signals that will be discussed in this lecture. Let's start by going back to the definition of a continuous signal. A continuous signal f is defined as shown, wherein we have two independent variables x and y, and this two independent variables is continuous as stated here. The signal can be represented and visualized in various ways. So your f here can be defined as the function or the signal, while xy, these two independent variables, can refer to the point of that specific signal. In imaging, your f here can or may refer to an image, while your xy here refers to a pixel, or in a 3D analog of pixel, we have voxel or volume element. So volume element, and this is picture element. In medical imaging, it is useful to have a mathematical model of a concept of a point source. This is due to the fact that we can characterize imaging system resolution using this one. A one-dimensional point impulse has the following properties. So this is the first property. Your impulse as a function of x, so this is your independent variable, is equal to 0 if your x is not equal to 0. And this is the second property. So the integral in all spaces of a certain function f with this independent variable x times your point impulse function dx is equal to f at x is equal to 0. In other references, this point impulse is also called the delta function. So delta function, or the Dirac function, and the impulse function. The point impulse is not really a function in the usual sense, but instead it acts on another signal through integration, as shown here. It models the property of a point source by having infinitesimal width. So we have infinitesimal width for this point impulse and a unit area. This unit area can be shown if this fx here is equal to 1. So just try to get the integral of this, and you'll get a unit area of 1. The 2D point impulse, also not a function in the usual sense, like the 1D point impulse, models the property of a point source located at 0, 0 by having infinitesimal width and unit volume, as shown in this equation. So we have two properties, same with your 1D impulse function. So the first property is shown here when your x and y is not equal to 0, 0. So thus the value of your function is 0. And the second property here is getting the integral of a certain signal f times your Dirac function here, which is equal to f 0, 0. So it's like picking off the value of this function fxy at the location 0, 0. So now let's suppose we shift the delta function to a certain position psi eta, which is just random Greek letters. So that is this one. You're shifted to the point impulse. So by getting the double integral over all space of this function f times your shifted to the point impulse, we will get this function. So it's the value of this function, of this signal, at the location psi and eta. So this is an important property of the point impulse, which is known as the shifting property. The signals derived from a point impulse can be illustrated as follows. So let's say we have here, just imagine that my drawing is perfect. So we have the x and the y-axis here. So think about this one as a plane, certain plane. So your Dirac function is located at point 0, 0. This uh, arrow here refers to this one. Your point impulse into D. Then if we shift this point impulse to a certain location psi eta, then this can be illustrated as this. So again, this is your x, this is your y. This is a certain plane. Then we just shifted your Dirac function in this location as shown here. So we have here your eta or your psi, and we have your eta here. Two other properties important in terms of point impulse is, first we have the scaling property. So for the scaling property, this is defined as your del function or your Dirac function ax by. So we have a certain constant here, a and b. This is equal to 1 over the magnitude or the absolute value of a times b times your Dirac function xy. So this is a scaling property. Finally, we have another property of this point impulse. This point impulse is an even function. So for an even function, so that is your Dirac function, so let's say negative x, negative y, this is equal to your Dirac function xy. So that is to say, we set your a, which is equal to b, to negative 1. When calibrating medical imaging equipment, it is usually easier to use a line-like rather than a point-like object. This is due to the fact that it is difficult to manufacture a certain equipment that is a point-like. For example, it may be easier to position a wire. So let's say we have a certain wire here, then we have this is placed on top of a certain imaging receptor. Then we have your X-ray source somewhere here. So it is easier to use this one than if we're going to use a small bead, let's say, placed on top of a certain imaging receptor in order to assess the resolution of, let's say, projection radiography. So resolution test. For this reason, we would like to have a mathematical model for a line source. So in this case, we have line impulse. So let us consider the set of points defined by this function. So in your x, we have this is a function of two independent variables, x and y, such that x cosine theta plus y sine theta is equal to L. This line impulse is associated to a certain line function as shown here, and this is the function of the line impulse. So later I will show to you how this one looks like. This function here is actually a line whose unit normal is oriented at an angle theta relative to the x-axis. So if we have here your x-axis, then this is your y-axis. So this is this line L from the origin. Then we have this theta, which refers, or this is relative to your x-axis. Then we can define your line impulse as this. So your line impulse is somewhere here. So that is your del L as a function of x and y. We have shown in the previous slide that we can use the shifted point impulse in order to pick off the value of a certain function at a single point. However, in almost all medical imaging modalities, we need to pick off values not just on a single point but on a certain grid. So, on a certain grid or matrix. And this is called sampling, which is important in medical imaging. So, we have this comb function uh, defined as this. So, comb x, this is equal to the summation of your Dirac function x minus n. And as you can see, this is a discrete function. So comb function, also known as the Sha function, allows one to represent both continuous and discrete phenomena, such as sampling or aliasing. And this is the two-dimensional form of the comb function. A Dirac comb actually is an infinite series of Dirac delta function. So let's say we have this comb function with a certain regular interval. Defining regular space intervals along the x and along the y, as shown here, allows us to define our sampling function as shown. This is useful in signal sampling, let's say for imaging. Also, we have the relationship between your sampling function and your comb function as shown in this last equation. And this is due to the scaling property defined for point impulse. So we can show this sampling function in a drawing. So let's say we have here your y-axis, then we have here your x-axis on a certain plane as shown. So we can have samples here or samples of impulse function on a regular interval. So along the y, we have delta y, and along the z, we have delta x as the interval.